Hello, good afternoon, everybody. Thank you very much for joining us today for this webinar. I see many people joining, so we might wait 1 minute more to start. I just take the opportunity to remind everybody that this webinar will be recorded and the proceedings will be then published online on the TREX website. Okay, so let's start. Good afternoon again. My name is Sara Pittonet. I am the Outreach Manager of the TREX initiatives, and I'm very happy to welcome you all to this webinar, TREX High Performance Software Solutions for Quantum Mechanical Simulations at the Exascale. The purpose of the webinar is to guide you all through the 6 different quantum chemistry codes and the open source libraries that the TREX initiative developed over the last 2 years. These codes are optimized for upcoming Exascale systems and ready to be integrated into quantum chemical codes, which could benefit from the Exascale transitions. You can find more about the TREX initiative in general at the web address that you can see in the slides, so trex-coe.eu. I just want to give you an overview of how many and how different institutes registered for this webinar. So this is a snapshot of the institutes that are represented today, both in terms of speakers, so representatives from the TREX consortium, but also of all of you who express your interest and are joining us today, and all those who registered from actually more than 26 countries over Europe and beyond. This is the agenda for today. So I'll soon give the floor to Claudia Filippi from the University of Twente. She is the TREX project coordinator, and she will give an overview of the TREX initiative. She will be then followed by 6 speakers who will give an overview of each one of the codes developed by the TREX project. So we'll have Ali Alavi, Director of the Max Planck Institute for Solid State Research, Kasia Bernard, Professor at the Institute of Physics at the Lodz University of Technology, Kuzuke Nakano, Research Associate at the CISA School, Ravindra Shinde, a Research Scientist at the University of Twente. Unfortunately, Emmanuel Gine could not be with us today due to an unforeseen health issue. He is from CNRS and contributed to quantum package code, but he will be represented by Anthony Shemama, Senior Researcher Engineer at CNRS, who will also introduce QMC Chem. And last but not least, Evgeny Pozenitsky will give an overview of the 2 libraries developed within the project. After these overview sessions, we'll give the floor to other speakers who will guide us through some examples of usages of the TREX code. So we will have Anthony Ferté from the University of Nantes, Pablo López Rios from the Max Planck Institute, Giacomo Tenti and Andrea Zen from the CISA School, and Stuart Shepard from the University of Twente. That's it so far. So I'm very glad to give the floor to Claudia Filippi, the coordinator of the TREX initiative, while I'll also invite you all to ask any questions you might have using the chat bar or the question and answer bar, and we'll go through any of your questions during the question and answer time below. So Claudia, over to you.
Thank you, Sarah. Can you see it?
Yes.
Very good. Okay, so welcome everybody. I will only say a few general words about TREX. So TREX is a center of excellence, which means that is a consortium funded by European Commission. So in TREX stays for targeting real chemical accuracy at the exascale. Okay, so we started in October 2020, and our focus has been on high accuracy quantum chemical approaches, and in particular on quantum Monte Carlo methods, so stochastic approaches in quantum chemistry, which are massively parallelizable methods. So you can think about multiple trajectories of Walker, which are sampling your wave function, where you can actually compute expectation value and project better approximation to the solution, the Schrödinger equation. So these techniques, use a relatively small I/O and memory, and for many purposes also relatively little communication. Okay, so the objective of the consortium is to make the codes, our codes, ready for Exascale system, and of course, we are also directly working on the codes which will be presented to you, but we decided not just to rewrite the codes, but also to provide some libraries. Okay, so one first library is actually a library of kernels for quantum Monte Carlo. It's called the QNCKL. Evgeny will present it later. And a second library which will exchange information, so wave function information between the code, and that's called TREX-IO. So now here is, a snapshot of the partners. So we are scientists from chemistry, physics, some machine learning experts. Of course, there are software and HPC experts. We have a communication SME. Sarah is indeed from such an SME, and we're having a technical SME, and also we're having representative of user communities. Now, only very few words about QNC, which is, a bit dominant within the consortium. They are not the only methods, as you're going to see, but let's say these are, also QNCKL is really focusing on sales approaches. And the idea is that you're dealing with the quantum interacting problem, but you're providing a solution which is stochastic. And if you look in the literature, you will find quite accurate calculation for medium-large molecules, and a bonus is that we can actually do periodic system, and that's an example from some partners inside our consortium of various electronic pairs in complicated materials. So the approaches are quite CPU intensive, but as I mentioned before, they can scale to actually massive parallelism. So generally speaking, of course, the fact that QNCs can be parallelized easily is in general not sufficient to have accurate results. And for us, this is also a very good moment because there have been a lot of recent methodological advances. For instance, we can compute analytical energy gradients. We're having a bunch of optimization tools for our wave function, and so the methods are actually can start to be treated as internally consistent with geometry and wave function, which are determined within the method. And also there's a lot of progress in working also on the expression of the many-body wave function, for instance, Geminas in TurboVB, but also, combining, neural networks with quantum Monte Carlo, as, you might find in the literature. So now within TREX, what we decided to do indeed was to create really a platform of codes and libraries. So we said, QNCKL, which covers, various, relevant QNC kernels, and it will have also a high performance let's say version, which can handle, CPU and GPU. TREX-IO can exchange wave function data between the TREX code, but also with codes outside the consortium, for example, games, PySCF, Gaussian, and more. And so you can also use the codes in a sort of pipeline. Okay, so you can start from a simple calculation, a DFT calculation, then import the data and do a quantum Monte Carlo calculation starting from that. Now, of course, the codes which will be presented have been modernized, refactored, improved, and also modularized to use these two libraries. In addition, TREX is also developing some machine learning tools which are integrated in our workflows, and our workflows are actually in turn integrated in the AIDA informatic framework. And this is to actually handle, to manage workflows, and also for HTC computing. And so the idea also that, via machine learning, we can also learn the accuracy of our method, maybe starting from cheaper approaches already available, whose code are already available within AIDA. So today we will focus on these codes. So for real space quantum Monte Carlo, we're having CHAMP, QNC equal to KM and Turbo VB. We're having a different flavor of QNC. So here we are really working in some sense in first quantization, so in real space, and here in orbital space, full configuration interaction QNC, and the code NACI. We are having then two deterministic codes. One is quantum package, can do sophisticated, select SCI, configuration interaction calculations, and also, a combination of DFT and multi-reference method, and GANCOR, which is specialized for the accurate computation of interaction of weakly, supramolecular system. And then, as I said, within TREX, we're not going to cover them here. We're also having machine learning tools and optimization tools of codes, Macau and Verificarlo, as well as some development to treat, to have, for cloud style access to HPC resources developed within MagWork. So finally, to conclude, we have a website. We have a very nice website where you can also find a lot of information about training. Okay, we offer training in the use of our codes, and you can also find a way to register through our website. And of course, there is the repository where we are keeping our software and where you can actually look it up. So, well, I will leave the floor to the next speaker. So we will start, with the presentation of the codes in TREX-IO library and QNCKL, and then move to the use of the codes. And I thank you for being here. And the next one is Sarah.
Yeah, thank you very much, Claudia, for this overview. The next one is Ali Alavi, director at the Max Planck Institute, who will guide us through the NACI code.
Okay, let me see if I can share this.
Yes.
You can see it all right?
Yes.
Okay. Thank you, Claudia, for the introduction. And I will say a few words about the NACI code, which, as Claudia mentioned, is a full CI solver, a stochastic full CI solver, which means that it is working within a quantum chemical description of the Schrödinger equation. And it solves, and the underlying algorithm which it uses to solve the full CI problem is full CI quantum Monte Carlo, which borrows heavily from diffusion Monte Carlo concepts that work within a real space description. So it imports into quantum chemistry, so to speak, diffusion Monte Carlo type concepts. But it solves the full CI problem, the quantum chemical Schrödinger problem. Now, a unique attribute of the NACI code is that, and this is the work that has been done as part of the TREX consortium, is it not only can handle Schrödinger type problems, but also the so-called transcorrelated or similarity transformed Hamiltonians, whereby we can introduce Jastrow factors obtained within from real space variational Monte Carlo methods. And the advantage of this transcorrelated description is, among other things, that it greatly accelerates the convergence to the basis set limit, which is one of the bottlenecks, if you like, of standard quantum chemistry. And in this way, we managed to combine, let's say, the first quantized approaches that normal VMC brings through these Jastrow factors with standard quantum chemical second quantized approaches. Now, the thing with the transcorrelated method is that it introduces a number of complications that you traditionally don't have when you're just dealing with the Schrödinger problem. And among those complications are that the Hamiltonian that you have to handle is actually non-Hermitian, unlike the original Schrödinger problem. And in addition, you have three-body interactions as well. These are introduced through the similarity transformations. And yes, the Nisi code, as we are developing it, has various ways of handling these three-body interactions as well. Now, the actual one of the aspects of full-CI quantum Monte Carlo is that it propagates walkers that are signed, so the positive and negative walkers, and these occasionally annihilate each other. They encounter and annihilate each other, so that you don't actually need to introduce fixed node approximations within the QMC sampling. We can also handle not only slated determinant representations of the wave function, but also spin-adapted representations as well, in which one can actually specify the total spin quantum number, not just the let's say the number of up electrons and down electrons, but you can target specific spin states with a specific S quantum number. And this is particularly useful in treating open shell quantum chemical problems with many open shell electrons. The Nisi code exhibits very good parallelizability, as I'll show on the next slide, up to about 20,000 processors. And so this is, I guess, not exactly exascale, but it's, pre-exascale type of parallelizability. And the output from the Nisi code can then also be used in various other approaches. For example, in the calculation of reduced density matrices, GAMCore can exploit those. And the wave functions could in principle also be exploited in other approaches. So I'll just, Pablo Lopez will actually show some examples of calculations running and results obtained using Nisi. But I'll just show in this slide an example of the parallel performance of Nisi. This is for some problem. It's a chromium dimer in a double zeta basis set. That's where you're correlating 28 electrons in 76 orbitals. So it's a fairly large quantum chemical problem. And what is shown here is the CPU time to execute a certain number of iterations, I think 100 iterations in a simulation with about 1.6 billion walkers. So that's a large number of walkers distributed over the processors. And you can see here we go up to, you have a log scale on the x-axis, and you go up to about 20,000 processors. And the amount of time that's lost due to load imbalance is, on the order of a few percent, which is quite small. Yeah, I think I will stop there. I think Pablo will later on in this webinar show some actual calculations using Nisi.
Thank you very much, Ali. Thanks for this presentation. So while I give the floor to Kasia Pernal to introduce the next code GAMCore, we have a question about the materials. Yes, so the recording and the presentations of today's webinar will be available as well on the event page on our TREX website. So Kasia, over to you.
Kasia, we don't hear you. You have no sound.
Yes, now you can hear me, but you don't see. let me start sharing again. Yes. So good afternoon once again. Thank you, Sarah. I'm going to introduce a deterministic code, which is one of the flagship TREX code, GAMCore. So GAMCore is not a QMC, but it's a quantum chemistry code. And after saying a few words about the capabilities, I will present the functionality of GAMCore on two examples. I'm going to stress the unique features of GAMCore. So let me first talk about two main functionalities of the code. So one is the electron correlation energy calculation, and this is dedicated to strongly correlated molecules. And the unique feature is that we can treat 10 to roughly 100 of strongly correlated electrons, which is really quite a lot, in up to 1000 basis set functions. And we have developed a unique method for computing dynamic correlation, which can be combined with a full CI DMRG solver or CAS SCF solver. I will talk about it later. And the other main functionality is, as Claudia already mentioned, molecular interaction calculation, where GAMCore provides not only the energy of molecular interaction energy, but also gives some interpretation as the interaction energy is split into physically meaningful components. So the unique feature of this functionality is that the method, which is SAPT, symmetry adapted perturbation theory, especially designed for strong correlated systems, it's applicable to systems which are weakly interacting. And they may be in excited states with local excitons, or they may be open shell systems, open shell molecules, or molecules out of equilibrium geometries, meaning that these are molecules with stretched covalent bonds. And these systems are challenging for other methods, which are not multi-configurational, but as I said, the SAPT, special SAPT, which is available in GAMCore, can easily treat such systems. So the other feature which is provided by GAMCore is that you can visualize dispersion energy in space, in real space, which also helps with the interpretation of what you are computing. So when it comes to interoperability of GAMCore, it is currently interfaced with MolPro, Dalton, Quantum Package, and Orca. So you can use any of these codes to produce wave function. And actually what we need is 1 and 2 electron density matrices. These are the ingredients, the only ingredients that must be loaded by GAMCore to start any calculation. GAMCore is also compatible with TREXio library. We will learn about TREXio later on today. And as I said, it requires only 1 and 2 particle density matrices, not higher than that. And this is actually why GAMCore is so efficient and it scales favorable with the number of active electrons. So when it comes to applications, I will focus on 2 examples. So imagine that we want to investigate interaction in molecules where one of which is in an excited state. Then you can run calculations with symmetry adapted perturbation theory developed for multi-configurational description of monomers. And as I said, you obtain interaction energy split into components, electrostatic exchange, induction, and dispersion components. And each of these terms have an interpretation. So we have a physical insight into their nature. So as I said, we not only get the number, but also the physics of the interaction. And here you can see the example of benzene cyclopentadiene dimer. And after excitation of benzene molecule, we create pi star exciton. So of course, the interaction energy between these 2 molecules will change. Using GAMCore, you can get the value of the change of the interaction energy, which is given here, but you can also investigate what actually has changed. And for this particular system, we could see that it was mainly the electrostatic and dispersion interaction energy components that have undergone major changes. So SAPT-MC, SAPT multi-configurational, which is implemented in GAMCore, as I said already, but I will repeat because we are quite proud of it, can handle up to 100 of active electrons in up to 1000 of base state functions for SAPT. And the wave functions that you can use for the monomer description, this must be run outside of GAMCore by one of the codes that I listed before, could be CAS-STF or CI or DMRG. The other functionality, as I said, is the computation of dynamic collection energy. And for this, we have developed a method which is based on adiabatic connection. The advantage over perturbational methods is that, again, we have much more favorable scaling with the number of active orbitals. So the calculation is very fast. And for the example of iron porphyrin, where we had 40 active electrons and 42 active orbitals, it took only minutes actually to obtain dynamic collection energy, which is really fast. So it's not only the efficiency, but also the accuracy, and the adiabatic connection method competes. It's even more accurate for some cases for bioradicals, for example, than perturbational method. So that's why we crossed out perturbation methods, and we recommend using adiabatic connection in GAMCore for dynamic correlation energy. Okay, thank you. I think I covered all I wanted. Thank you for your attention.
Thank you very much, Kasia. Let's now move on to Turbo RVB, and I invite Kozuki Nakano, Research Associate at CISA, to present.
Can you hear me?
Yes.
Okay, so I'm introducing Turbo RVB, which is our one of the real space quantum Monte Carlo source codes. Okay, so our Turbo RVB packages consist of three, let's say, softwares. One is Turbo RVB, which implements quantum Monte Carlo kernels, such as density functional theory, including density functional theory and variation Monte Carlo and diffusion Monte Carlo. And the other tools are Python packages, which are for users. So Turbo RVB, the main developer was Professor Sandro Salella, and it has been developed for over 15 years in CISA. Now the project PIs are currently Michele Casula in CRRS and I. The most important message is in this slide is Turbo RVB has been developed in CISA internally, but will be open source by July 2023. As Claudio mentioned, Turbo RVB implements two real space Monte Carlos, variation Monte Carlo and lattice regularized diffusion Monte Carlo. Another feature of Turbo RVB is we can use flexible ansatz, such as anti-symmetrized geminal power and Paphian, by which we can go beyond standard Slater determinant, which means we can consider more electron correlation. Another prominent feature of Turbo RVB is we can compute atomic forces by exploiting the algorithmic differentiation developed by Sandro Salella, which is very important for material science and condensed matter physics research. Last but not least, Turbo RVB is parallelized by MPI, OPMP, and GPU, so which is very suitable for application on high performance computers, exascale computers. Okay, so here I am showing an example of Turbo RVB calculation, the potential energy surface of a very challenging dimer, the carbon dimer. So as shown here, the binding energy computed by Slater determinant is far from the experimental value shown here, which means the electron correlation is not sufficiently taken into consideration within this Slater, just for Slater ansatz. However, in Turbo RVB, as I told you, we can go beyond the Slater determinant, which allows us to reach the very close value to the experimental one. So we can, by using Turbo RVB, we can study highly strongly correlated materials, molecules and crystals. And here I am showing another example about using the atomic force calculations, because So, I mean, using TurboRBB, we can access physical properties derived from atomic forces, such as phonon dispersion calculation or molecular dynamic simulations. Probably later, Giacomo is going to talk about the application of in this sense. So here I'm showing, as I mentioned, we have recently developed Python packages, one of which is Tab Workflow. So this was developed for, say, for user, sure, because now we can implement workflows on a Python script like this. So now we can so here, okay, I'm showing here the example of potential energy surfaces of the carbon dimer. So we used to compute them by hand at each bond length, but now thanks to Tab Workflow we have developed in this TREX consortium, we can implement workflows that we would like to compute on one single Python script, and then Tab Workflow, which is interfaced with TREX.io, can automatically solve the dependencies defined on the Python script and can monitor also the calculation. As I told you, the Tab Workflows is interfaced with the TREX.io. We can also start from the calculation. For instance, from PySCF or Gaussian or other DFT codes now. Okay, here, so as I told you, if so the TurboRBB will be open source in July 2023. But if you are interested in, you can visit our website and request request a permission to access the repository. Thank you very much.
Thank you very much, Kazuke. And now it's the turn of Ravindra Shindre, who will present the CAM code. Do you want me to share the slides, Ravindra?
I can share it from here.
Okay, great. And there is a question by Max Wilson that we have noticed, but we'll keep it for the end of the series of presentation of the codes since it's relevant for everybody. So Ravindra, go on.
Can you see
Yeah,
my slides?
we can see it, yes.
Okay, thank you. Hi, I'm Ravindra, not Claudia. I'm using her computer. So I'll be presenting CHAMP code in this webinar. So CHAMP stands for Cornell Holland Ab initio Materials Package. It's mainly developed at the University of Twente, the Holland branch of this code, along with some European collaborators. And it is a quantum Monte Carlo suite of programs for doing accurate electronic structure calculations of molecular systems. And we are currently developing for the periodic systems as well. CHAMP specializes in a variety of features. To mention a few, we have efficient optimization scheme for ground and excited states in VMC. We have recently implemented a state-specific energy minimization in VMC. So, and Stu will be elaborating more on this later in this webinar. Also, we have efficient analytical interatomic forces in VMC. We also have fast evaluation of multi-determinants and their derivatives. And lastly, we have multi-scale hybrid QMC features, so you can do multi-scale calculations along with QMC. To elaborate further on those features, I will be giving some examples for each one of them. So, for example, for efficient analytical interatomic forces in VMC, we'll take an example where with an increasing increasing size of the system, along with increasing number of determinants, we can calculate the energy as well as forces with just 3 times the cost of the calculating the energy only. So for a wide variety of system complexity, you can just calculate forces with 3 times the cost of energy. Also, we can calculate we can do a wave function optimization because of the fast evaluation of multi-determinants and their derivatives. So similarly here, we can calculate the energies as well as derivatives of wave functions for a large number of parameters in the wave function with just a cost of 3 times the VMC energy. We can combine both geometry as well as wave function optimization for ground as well as excited states. Here, this is the geometry optimization along with wave function optimization for the 200 optimization iterations for this molecule. And you can see there are like 200,000 determinants in the wave function and 65,000 wave function parameters in total. Similarly, we have state-specific energy optimization, which was recently implemented by Stu and other members of the group. In this case, we can have optimization of each state independently. We can also accurately describe double excitations using CHAMP. As the case with other codes, we are integrated through TREX IO with other codes of TREX consortium, as well as the other codes of quantum chemistry, such as GAMES, Gaussian, MOLCAS, etc. We have also incorporated a QMCKL library inside the CHAMP code. We have improved vectorization in the CHAMP. And this is the scaling, a typical scaling on a supercomputer. And you can get this code, the QMCKL as well as TREX IO codes on this on GitHub of TREX COE. And if you want to collaborate with us, you can just drop an email and the code will be made available to you. And thank you very much.
Thank you very much, Ravindra. So I see there are some questions in the chat. So I propose that while our speakers take a look at the chat, I invite Anthony Shemama to give an overview of the last 2 codes. And then we keep the questions for the end of this series of presentations. So Anthony, over to you.
Okay, so so hello everybody. So I'll present first quantum package. So quantum package is a deterministic code. So just like NICI, the goal is to try to get the full configuration interaction energy. So FUCI is the exact solution of the Schrödinger equation, where the only approximation is the 1 electron basis set incompleteness. So basically, you get the exact solution for a given basis. But the problem is that FUCI is intractable. So that's why NICI solves it with a Monte Carlo algorithm. And so what is important is that all the traditional methods of quantum chemistry try to approximate the FUCI. So that's what we're also trying to get. So if you look at the literature today, the largest possible FUCI calculation that has been done was 24 electrons in 24 orbitals, which is quite small in terms of systems, but it represents 900 billion determinants. So it's really a huge calculation. So you really see that with the factorial scaling, it's really hard to reach. And recently, some selected configuration interaction algorithms have been more and more developed. And now you can see on this paper that you can do 44 electrons in 44 orbitals just on a single node in a few seconds. So these selected CI algorithms are very, very powerful, and this is exactly what quantum package is doing, using a selected CI algorithm to try to solve to get the full CI energy. So I represented here the CIPC algorithms that we use. So basically, we start with a single determinant, and we try to find what are the determinants that will be the most important to reduce the energy. We include them in the internal space, diagonalize, and then we iterate And we iterate with more and more and more determinants until we reach we have included everything and reach the full CI. So in terms of graphics, you have here the number of determinants and here the energy. So here I represented two states, so the ground state and the excited state. So that's the variational energy. So you start here with a small number of determinants, then you add a little more, then you add a little more, and every time you add the most important ones, the ones that will make the energy go down faster and faster. And you see that here you tend to converge to the full CI energy for the ground state and similarly for the excited state. And the curve you have here down is the PT2 correction. So it's a perturbative correction to try to estimate the full CI energy. And so you see that that this energy converges. And what is important is to really see that this perturbative correction, when you have reached the full CI, it is zero. Okay, so basically you can use this feature to extrapolate and estimate the full CI energy. So typically this is what we do. We plot the energy as a function of the PT2 correction and we extrapolate to zero, and this is how we can estimate the full CI energy. So on this system that I've shown here, this little molecule, in the basic set we have chosen, the full CI wave function would have needed 10 to the power 25 determinants, which is enormous, and you can see here that we can use 100 million to get the energy. So we really take a little fraction of the space and we can get very good estimates of the energy. So that's what quantum package is doing. So you see that these calculations are quite expensive. So here we have been parallelizing quantum package and running up to 12,000 CPU cores. But the thing is that it really requires a huge problem to use such a scaling. So typically we're more in this region where we use like 2,000 cores. But also, as the size of the space is growing with time, we can add more and more resources to accelerate the calculation dynamically. So it's a kind of special feature of quantum package. So typically the applications we do are to make benchmark, to provide benchmark values for some systems, so that people who develop some approximate methods, they know what number they should obtain. So here we have done some calculations for excitation energies, a large benchmark, where we have also given this QuestDB, a database of excitation energies, also correlation energies for 5 and 6 member rings, and now we're also providing some full CI quality properties. So it's important to mention that it's an open source code, so it has been designed to help the users to develop new methods. So it's more a programming environment than a code that you would use as a black box. And so the users are encouraged to develop their own plugins so that they can redistribute their plugins, and that's the way it works. Okay, so that's it for quantum package. So it produces some very accurate wave functions, and this is a good transition to go now to QMC-Chem. So QMC-Chem is a quantum Monte Carlo code that can do very few things, but can do them very well. So it can do VMC and DMC for very large CI expansions, ground and excited states, all electron or pseudo potential calculations, but with the determinant localization approximation. It can also optimize very large CI expansions in the presence of a Jasper factor, and it's well adapted to massively parallel machines. And so what it cannot do periodic systems, T-move with pseudo potentials, sophisticated Jasper factors, backflow, JAGP, nuclear forces, all this it cannot do, but it can do very well this part. So the idea of QMC-Chem is really to compute what we call a block. So a block is really a given number of trajectories in parallel on a single CPU, and for a given number of steps. So each CPU will compute one block, then in Winston will compute another block and another one until the termination condition is reached. And we will do this in parallel on thousands of nodes all together, and then we do a big reduction to sum all these statistics together. That's the way it works. So the design of the code is the following. So you have a server, a main server here, where on each on the server node you will run some QMC processes to make to compute some blocks. Then on other nodes, on the compute nodes, you run also some QMC processes that compute blocks, and then regularly they send their data to the data server that accumulates everything and stores some reduced data on disk. And so you see, with this design, you can at any time add a new compute node, connect to the data server, and contribute to the calculation. So you also have this dynamical resource management possibility. And also with this design, you see that if some compute node is dead, you just lose some statistics, but you don't kill the whole simulation. So to enable this fault tolerance and dynamical resource management, we use ZeroMQ for communication instead of MPI. And also what is important is that the wave function that we give to QMCChem comes from quantum package, so it's quite a strong restriction. So in terms of HPC, we've been doing some large-scale applications. So we have almost reached the petaflops in 2011 on using the Curie supercomputer on a very large number of cores. And then later on, we have been doing some distributed HPC and cloud calculations because using these libraries, we can easily go to non-HPC systems. So a small application, small but important application we have done was this one on the water molecule, where we have been able to give the reference reference non-relativistic energy of the water molecule. So we have shown in this paper that so these are Fuchs-CI calculations that were done with quantum package, and using these trial wave functions which were near Fuchs-CI, we were able to use these huge CI expansions with millions of determinants as trial wave functions for QMC. And then when we were running the diffusion Monte Carlo calculations, we have seen that we also converge to the exact energy just by increasing the basis set. So I put on this slide a few applications that were done with QMCChem, and when you will download this PDF, these links are clickable, and so it can redirect you to the papers. Thanks for your attention.
Thank you, Anthony. Let's close this series with Evgeny Kosinitsky, who will guide us through the libraries. Over to you, Evgeny.
Right. Okay. Can you see the screen?
Yes.
Okay. So hello, everyone. My name is Evgeny Kosinitsky. I'm a previous member of the TREX Center of Excellence, where I was working at CNRS in Toulouse with Anthony Simama. I'm currently working in a French startup called Qubit Pharmaceuticals. And today I will present the TREX open source libraries, which have been mentioned already. So there are two of them, TREX-IO and QMCCale. So I will start with the TREX-IO, which is it's actually a library and an IO format. So it comes in two flavors. And so I will first talk about the format, and then I will say a few words about the library, which is, yeah, it's the same thing. Right. So why do we want yet another format? So when the TREX project started back in 2020, this is how the typical data workflow would be organized between the TREX flagship codes. So you can see that it's a bit convoluted, and what is more important, there are some blocks that are common between different codes. And so in the past, like what is common in quantum chemistry community, each code would have its own representation, and so it would have its own input file, and so basically one would have to write converters to process the output of one code and to get it as an input to another code. So this is a lot of extra work which developers have to do, and especially they have to track the changes in the output files. So it's a very cumbersome work. So we have introduced the TREX IO format, which was initially developed in order to unify the wave function data exchange between the TREX codes. So we have identified the common blocks that are common between our codes. So we organize them into groups, and then each group would have several data blocks. So for example, to describe the atomic configuration of a molecule, we would need a nucleus group, which would contain the number of nuclei, atomic charges, coordinates, labels, point groups, and nuclear repulsion. So here you can see an example. It's a sample of the real, of the full TREX IO JSON file. So we chose JSON as a kind of intermediate representation for the format because it's this format has been adapted by the community, but it's just a way to represent the format. So it allows us to divide data into groups, blocks, and assign data type and dimensions to each block if needed. So you can find a full list of all groups and data blocks in the TREX IO documentation. I will not go into details of that, but so far we have all the blocks needed to describe single and multi-determinant wave functions, and we have started extending the format for periodic boundary calculations, in particular for turbo RVB. So a few words why we decided to, about the things that we believe are done differently in TREX IO compared to some existing wave function formats. The most important thing here is that the format is fully self-consistent. So you don't need any information about the code that produced the TREX IO file in order to interpret it. All the information about basis sets, atomic orbitals, integrals, everything you need will be stored in the file. And so you can easily share it. And then, as I said, there is no code-specific information needed to process the data. We have normalization parameters to cover some existing ambiguities. So we worked on compact storage of sparse quantities like 2-electron integrals, reduced density matrices, CI coefficients and determinants, and other features. And what is more important here is that there will be no custom text-based formatting. So you can forget about the typos in the input or output files and all the changing formats whatsoever. So now a few words about the library, because the TREX IO format is a kind of, you can think about it as a container. So it comes, once you're given a file, you would want to extract data. And so for this, we encourage our users to use the API, which is actually the way to interact with the TREX IO format. So the API is written in pure C, which provides us the best performance and portability. So the code has two backends. One is based on the HDF5 library, which is became de facto standard for high performance IO, and it does provide a lot of enhancements to the IO that we perform. And a second backend, which is more like a debugging version, which is a pure text backend, which is producing ASCII files. But again, you don't have to go and manually inspect these files. There is an API to get and write data. So that's the only way. And then we have developed several bindings. So we have a Fortran, Python, and OCaml interfaces And TREX, so we have invested a lot of time in making TREX easy to install. So you can find it on almost any package manager that is currently used in the community. And you can, of course, install it also from source using AutoTools or CMake build systems. So the source code is on the TREX COE GitHub, and you can go there and find more details about the installation. So the situation as of today is that all flagship codes can communicate with the TREX.io files. Quantum package as a deterministic CPC code can produce TREX.io files that can be further processed by almost any other code. And we have also a coupling between TREX.io and QMCKL. So just a few words about the nice new exciting projects that were enabled by adoption of TREX.io. So first of all, of course, we could unify the data exchange and we could improve the I/O performance, which was very important for us. By using the CPC wave function and density matrices, we could enable the GAM core to do SAP with CPC wave functions, and CHAMP could do QMC with CPC wave functions. So as has been mentioned by Ravindra, CHAMP and actually all TREX.io users are interfaced with GAMS, Gaussian, and PySCF because we wrote converters from the output of these codes into TREX.io. And another nice feature of TREX.io to QMCKL integration is, for example, that one can easily write user-friendly QMC tutorials in pure Python. And these tutorials will actually run fast because they will use the pure C code underneath. So a few words about the QMCKL, which is a Quantum Monte Carlo kernel library, which have been mentioned already in a few talks. And so it provides an API for main algorithms of Quantum Monte Carlo, both in pedagogical and high-performance implementations. So it provides low-level and high-level functions which are optimized for the user. So they are tailored for the performance on a target machine. So the user doesn't have to care much about it. And there are bindings in C, Fortran, and Python already available for QMCKL. And so we've seen already how adoption of QMCKL has improved the performance of CHAMP code. Here is another example of it's more like a use case which was performed by another previous TREX member, Vijay Chilkuri, who is now at Aix-Marseille University. So Vijay and coworkers performed, so they have implemented an optimized Jastrow factor in QMCKL, and you can see the performance, the speedups they could achieve for various number of electrons. And so it's actually a remarkable acceleration already. And there is also a custom version of DGEM, so the matrix-matrix multiplication, which Vijay and coworkers also worked on. And we believe that this curve can be further improved by adoption of this custom DGEM. And there will be more papers coming on this in the near future. So with this, I would like to conclude. Thank you for your attention. And you can find the source codes of both libraries on open source on GitHub. Thank you.
Thank you very much, Evgeny, and thank you to all our speakers so far. So while we get ready for the second part, I'd like to take the question that Max Wilson asked to all our speakers. So it's a general question. Where do you see the largest potential improvements when scaling to Exascale? So there is then a longer description. So these codes must be close to theoretical optimal. So are they low-hanging fruit in terms of performance? So I'd like maybe to ask our speakers to respond to Max so openly. So is there anybody who wants to take the lead?
I can take the question if nobody wants to. So I really think that the Exascale systems there will be the use of an Exascale system will be different from a petascale system because there are almost no codes that will be able to make a single run on the whole machine and take advantage of it. So to use efficiently an Exascale system, the way to do it will be to run a large number of petascale simulations altogether. So, for example, if you want to perform potential energy surfaces, then you will be able to make a petascale simulation for each point of the potential energy surface, and you can run all of these independent calculations in parallel. In the same way, if you want to do some benchmarks like what I'm doing for excited states, I would be able to run thousands of calculations in parallel with very high accuracy. And another very important point is to produce reference data that will be fed to machine learning systems. Because machine learning will work if you have a large amount of data, and with this Exascale system, we'll be able to produce this very, very, very large number of data. So I think in terms of code, that's the way we will have to adapt, and it's also the reason why we integrate all our codes into workflows like Kosuke has shown, or in the IDA system of workflow, because the users will now need to be able to run complicated workflows, transferring data from one code to another to produce these very large data sets. So I hope I answered your question.
Thanks, Anthony. I'll let Max confirm if he has any further questions. Then there is another question by Michele. I believe it's for Evgeny, but I'm not sure. So what is the origin of the jump in the speed of the Jastrow calculation in QMC KL? And I can also allow you to speak, Michele, if you need. Michele is one of the developers also of the.
I think maybe Anthony has
or
more.
Anthony. Okay.
Oh, okay. So I can explain the jump. So this is because we took the implementation of jump of the three-body term of the Jastrow factor, which was known to be not super efficient. This is why we worked on this part, is really because it was a part which was critical to optimize. And the way it was written was not really adapted to large to do thousands of electrons. I don't even know if Claudia has ever tested this three-body Jastrow on thousands of electrons. But the thing is that it was doing some access to arrays, and when the arrays become too large, then you start to do some cache miss, more and more and more, and at the end you even do some page miss. And so this is why you have this jump. It's because the naive implementation was becoming more and more inefficient with the size of the data. And the implementation that we have done for this part is heavily relying on DGEM, matrix multiplications, for which the usage of data is really good. And so this is why when we use the DGEM, we are almost constant in terms of performance, but with the naive implementation, we get inefficient when we get out of the caches. And also, you can remark that there is a linear, it always accelerates. And this is because we reformulated the initial formulas in such a way that we were able to get an order, a constant order n on the formulas. So we have a better scaling with number of electrons.
Great, thanks. There were another couple of questions that were directly answered by Kozuke and Anthony about specific codes. So I don't know if there is anything else that you want to mention publicly, Kozuke, or I mean, anything further. If not, I suggest that we move on to the second part of this webinar. So I welcome now on our virtual floor Anthony Ferté, who will give us an example of usage of quantum package.
Do you see my screen? Is it okay?
Yes, it's okay.
Okay, perfect. So good afternoon, everyone. So I'm Anthony Ferté. I'm currently postdoc in CESAM laboratory in Nantes. But if I'm talking to you today, it's because I've been a quantum package user since 2018, so almost 5 years. I came in contact with a quantum package for the first time during my master internship, so that I did in the LCT laboratory. I did it with Emmanuel Giner, which is with Anthony, one of the two main developers of the code, and also Julien Toulouse, and we were working on also multi-determinant range separated density functional theory, and did the implementation in quantum package. After that, I went on in the LCPMR lab where I did my PhD. This time with Stéphane Carniato and Richard Taïeb. And this time it was, I was working on a theoretical description for double core Hall spectroscopies. And contrary to my master internship, I was not working with original quantum package user, but I still decided to use this code in my study. So just a few ideas, like what I was actually doing during my PhD. So the subject of my, the main subject was those kind of spectroscopy. So XPS, X-ray photoelectron spectroscopy, was where we use high energy X-rays to excite a molecular system, for example, CO2, and we remove core electrons and we detect spectra. So XPS is a very well-known spectroscopy, but since something like 10 years, there have been a huge development in X-ray sources that allow to go further in those methods. And more specifically, what it allows us to do now is to remove more than one electron. So that's why those double ionization and excitation. But my PhD was also interacting with other field of chemistry, so quantum chemistry, which provides the theoretical framework, the mathematical equations that describe the system and the spectroscopy, and also what is more the subject of this webinar today, which is computational chemistry, where we use quantum chemistry software to solve those equations. So that's where a quantum package came into play. Yeah, so why did we need to do development for that? So when you do core electron spectroscopy or double core spectroscopy, you have your X-ray, which remove two core electrons from the system. And so you create a double electronic vacancy. And because of that, the system needs to readapt, to relax to that strong perturbation. And it leads to a strong modification of the electronic cloud. So this is what I show you here for the case of a CO molecule, where we have done a double core hole in the oxygen. And what we see is that there is a huge increase of electron density in the vicinity of the oxygen atom, because there is this double vacancy. Because of that strong relaxation, there is a problem. It is that we cannot find one specific molecular orbital basis to describe both the initial, the neutral system, and the final, the double cationic system. And it is a problem because we like to use the same molecular orbital basis because it leads to a lot of simplification due to orthogonality. But it's a huge problem in this case because if we try to simulate the spectrum, we get some things that look like the green one, the dashed curve here, which when we compare it to the experimental result, which is in black, give completely wrong answer. On the other hand, if we make the effort to use different molecular orbital bases for neutral and cationic system, we can get pretty good results, which is what I show you in blue, which is a result that came from my calculation. But for that, I had to develop all computational structure to deal with that non-orthogonality. And this I did it inside Quantum Package. So why did I choose to use Quantum Package? Actually, it was not a choice by default. As usual, when I started my PhD, I tried to use programs that were that my advisor were using. But quickly, I came to the conclusion that it may not be the best choice for me, and I moved back to Quantum Package. And there is many reasons for that. The first one, and the main one for me, is that Quantum Package is not a program that fight back when you try to do new stuff. As Anthony said, it's a program that have been created with the idea of making more development platforms than a program, and because of that, there is a lot of flexibility for developing new stuff. It's also its structure is very user and developer friendly, so it's developed using this extension of Fortran, which is the IRPF90, which allow to implement and interface with what exists already in the code in a very simple way. It have also very nice features, so simple I/O system, and also a plugin system, which is always nice when you do development, because if you have a code and you do modification, it is in its source code, but then you want to export your development in another program, you will not just take your subroutine and stuff like that. It's easy to have a system that does that for you. Yes, and also stuff which is very useful when you are developing is that it's usually simple to find the documentation for which are relevant for developer. Especially for my subject, so core spectroscopy, because Quantum Package was created around that idea of selected CI, all its internal structure is made to handle Slater determinants, which is a very good point for me, because I wanted to handle the determinant, and especially I wanted to remove electrons. So this is one of the points I liked. And it also allowed to produce a high quality wave function, and so high quality spectra, and also to analyze and understand the physics that is behind. Few other bonus from the code. So there is a helpful and friendly team. So Anthony and Emmanuel always ready to answer questions. And also it's a free and open source software, which is always nice to see. So in how did I use actually Quantum Package? So I did a different application with it. So there was a methodological aspect. For that, I developed, well, there was two things. So first, I tried to adapt the way Quantum Package worked to do those calculation, core calculation. And also I developed a large series of plugins mainly to deal with this non-orthogonality, but also to do some interpretation. So as a simulation, I had a lot of interaction with experimentalists, where they were giving me different kind of spectra, and I could simulate them very efficiently. So here on the left, it's a standard XPS. In the middle is a double core hole, and also other new kind of spectroscopy. Other type of simulation like dynamic, and all of that came straight from Quantum Package. So just thank you to everyone, especially Emmanuel to introduce me to this code, Anthony for the invitation, TREX for the organization, and everyone for your attention.
Thanks, Anthony. Thanks, Anthony, for the very nice overview. We are running a little bit late. So I call Pablo now to give an overview of his experience with NISI.
Hi. So, yeah, so I'm more a developer than a user of electronic structure codes. So that's why I'm going to present as an application more of a benchmarking type set of results than you would otherwise see from, well, from other like regular users. And if I find it, then that should be that. So I'm focused mainly on the combination of real space and second quantized type quantum mechanical methods, like so VMC and DMC with FCI-KMC, for example. And the transcorrelated method is one of these places where these two methods meet. And so that this is sort of a natural type of methodology for me to play with. So because I come from a background of VMC and DMC, so I'm one of the main developers of the casino code, which is not part of TREX, but that makes the implementation of the Jastrow factor evaluator in casino a natural choice for me to use in our pipeline. So this would be the workflow I'm showing here that we use to run our transcorrelated FCI-KMC calculations. We use PySCF, which is an open source code external to TREX as well, to obtain our orbitals. And we optimized a Jastrow factor using the casino code, and we plug that into our own library called TCHint, which evaluates well, up to 3 body integrals that we need to run the FCI-KMC calculations later on. So one of the things we then want to do in the future is to get rid of casino from this workflow, because casino is itself proprietary code. So and I want to highlight that one of the opportunities presented by TREX and this type of collaboration effort is that we are now able to choose among different codes to replace casino with. And I mean, there are all the codes in TREX and there's also the QMCKL library that we could use. And also there is the possibility granted by the ability to give our code to people for optimization. Then we get code that is a lot faster or a lot more efficient than before. And that has actually been the case, not exactly within TREX, but with other external collaborators. We can give our TCHint library to someone, a computer engineer who can optimize the code, and they have, and now our code is 100 times faster, and we get to actually decide to re-implement the Jastrow factor optimization into TCHint itself without having to use Monte Carlo at all. So that's an interesting thing that we can do that I wanted to highlight. So the results that I want to show are basically for just 4 small molecules, for which I mean they are not by no means simple to handle. And so basically what I'm showing here in these 4 plots are total energies, well, atomization energies, more like, versus the inverse of the number of orbitals in the basis. So basically, as we go to the left, we go to the complete basis set limit. That means we go to an infinite computational cost when we get exactly to, well, where the infinity sign is. And but we also get more accurate. And the point is that with transcorrelation, we get within the gray area, which is basically the best estimate of the atomization energies for these 4 systems, a lot quicker than without transcorrelation. So the use of Jastrow factors, which is a first quantization object in a second quantized methodology, is a very advantageous thing to do. And so all of this, each of these data points, by the way, has been pushed to the full CI limit by extrapolation, very much like Anthony mentioned earlier, right? So we are using a technique we are developing to get to the full CI limit. And so basically, yeah, that's the key takeaway. So with this workflow that we have using this all these codes, we can manage to with a lot less computational code run a TC FCA-QMC calculation and get a very good accuracy with a lot less effort. And that's all I wanted to say for today.
Thanks, Pablo. We have another couple of experiences now called the CISA colleagues, Giacomo Tanti, Andrea Zen, talking about Turbo RVB.
Okay, can you hear me?
Yes.
So I'm Giacomo Tanti. I'm a PhD student at CISA, and I'll briefly talk about my experience with the code the Kozuka I presented before, that is Turbo RVB. So my experience with Turbo started with my master's thesis, where I studied a nitrogen chain using the Pfaffian wave function. That's actually one of the features of the Turbo RVB code. And I would say that I learned to use Turbo the hard way. This was because this particular type of problem had a very complex workflow. In Turbo, there are in principle lots of parameters to control and lots of files. You have to learn how to handle these files, and it can be very complicated as a first-time user. But I would say that this worked only because of Professor Sandro Sorella. That was the one that taught me how to do that. But I think that I think that right now that there is an easy way that is the way I recommend, like that I recommend to follow for a first-time user of Turbo, that is actually using Turbo Genius. That is a very nice tool that now we have, is actually a Python package that allows to extremely simplify the workflow of a typical calculation in Turbo RVB, so that even a user that is the first-time user can somehow focus on the only the parameters that that are interesting, and more or less simplify the typical workflow of a typical calculation. And moreover, something that I really like about this is that an advanced user can still have a complete control of the calculation and all the parameters if you wish to do that. I will just briefly talk about some of the projects I've been working on using Turbo. And this first one is the structural optimization in one-dimensional carbon chains and the study of broken symmetry states where you have a bond length alternation, and even states where you don't have a bond length alternation, but you have a charge density wave instability. And you can study this type of system with Turbo very nicely, thanks to the possibility to perform structural optimization and also to control the symmetry very easily, to control the symmetry of the wave function, to study, for example, these more exotic states like charge density wave states. Another application is that is somehow related to the work I did in my master's thesis. There is the study of hydrogen model systems. The one I showed here is, for example, the study of the phase diagram of a 2D square lattice. That, of course, is the direct generalization of the hydrogen chain in 2 dimensions. And also in this case, the very nice thing about Turbo is that you have you can control the symmetry, so you can, for example, study broken symmetry phases like antiferromagnetic states and so on. And you can also see how, for example, the description of the system changes by using more advanced wave functions, such as the Pfaffian, for example. And finally, let me talk about an application that is more related to realistic system. It's also related to Turbo workflow. That is this other tool that now we have to somehow organize large-scale computation. And for example, in this application, we can directly generate with the QMC data sets to be used to train machine learning potentials. And this is a work that we did together with Kosuke, Andrea Tirelli, Michele Casula, Professor Sandro Sorella, where we trained machine learning potential on QMC energies and forces that Turbo can compute very efficiently, and using that, and also pressure, this is very nice, and this I think we can further develop this type of calculation with the exascale transition. This type of application will be very prevalent. With this, I think
yeah, thanks.
Give the word to Andrea.
I kindly ask our participants to stay a few minutes more, so we give the floor to both Andrea and Stuart. So we'll take 10 more minutes of your time.
Hello. So do you see my?
Yes.
Okay.
Yes.
Good. So thank you for inviting me to talk about my experience as a user of Turbo R2B. Turbo R2B has a very nice feature that I have used in the past and I'm still using. It allows to use an ansatz that is implicitly multi-determinant. So I mean, the typical ansatz that they use in quantum Monte Carlo is a single Slater determinant with just a factor that recovers for the dynamical correlation. In Turbo R2B, there is an answer that generalizes this. And it is discussed very well in a review paper that it was published a few years ago, this paper that there is in the slide. And it shows as the single Slater determinant is a particular case of a more general ansatz, the Pfaffian ansatz, and in between there are other levels, other ansatzes that are more general than the single Slater determinant, less general than the Pfaffians. This hierarchy of ansatzes can be used to have a better description of a physical system. And so the question is, well, but do we need this? So when do we need to go beyond the standard answer, the single Slater determinant with just? I mean, general answer is when there is strong correlation. But here I'm reporting 2 examples of systems that I also investigated myself. One is, for instance, when there is bond breaking. For instance, a molecule of ethylene which has two carbon atoms and 4 hydrogen atoms. In the ground state configuration is flat, but if one twists the hydrogens, the twisted configuration at some point of the HOMO and LUMO levels that are degenerate, and this configuration cannot be well described with a single slater determinant. So even using diffusion Monte Carlo, so the fixed node projection scheme, one cannot improve this problem of the single slater just a wave function, while the AGP can give very good results. So in agreement with the no exact results. And similarly, in transition states, so like this is, sorry, the ethylene case is an example of bond breaking, because in the planar configuration, the carbons have a double bond, and when one twists them, the one of the bonds, so the pi bond gets broken. Another example is in transition states. So the example that you see on the right is the case of the retinal chromophore. So in the process of vision, there is a molecule that has a conformational change, and this triggers the process that allow us to view things. And in order to understand the mechanism, it is important to measure the barrier that there is between these two conformations. Even here, we need an ansatz that is more general than a single slater determinant plus Jastrow to have a reliable barrier. And now I want to mention about a project that is a work in progress. So the point is reference methods for non-covalent interactions. In quantum chemistry, the reference method is considered a couple cluster with single, double, and perturbative triples. But also quantum Monte Carlo at the fixed node projection level is also considered a reference method here. And in general, we see very good agreement between the two approaches. Couple cluster used for smaller molecules typically because they have different scaling with the cost scales differently with the size of the system. So couple cluster is cheaper for small system. Quantum Monte Carlo is cheaper for larger systems. And in between, like one see the agreement, but recently there is a paper here that showed that there are some systems where there is quite big disagreement, and it is unclear why there is disagreement, where it's coming from. It might be that there is a problem on quantum Monte Carlo or in a couple cluster, but as a quantum Monte Carlo user, I'm trying to understand if I see a problem in quantum Monte Carlo. And my guess is that if there is a problem, it should be at the level of the ansatz, because the ansatz affects the fixed node approximation. There is a difficulty here in this interaction, in the evaluation of the interaction energy. Here we are doing the difference between two or more molecular systems where the total energy is much higher, larger than the interaction energy. And so one has to be careful to have a description of the system when that's the difference that is consistently good. And is not only on the quality of the ansatz, but also practically in having a control on the optimization. Because in the optimization, if there is a stochastic part in the optimization, the stochastic noise could be larger than the interaction energy that we want to evaluate. And so here, that's the point where we also are have a benefit from the TREX IO, because in this project where also Kosuke is involved, we are using a code like by SCF, which is standard with the standard quantum chemistry with deterministic, approaches. And then we convert the output to go into one of the generalized ansatses that we can use on Turbo. And I hope that at some point we will find a solution for our problem. So
Thanks, Andrea. And last but absolutely not least, I'll give the word to Stuart.
Thank you. Good. Okay. Hi, I'm Stuart Shepard. I'm a postdoc in the group at University of Twente that works with the CHAMP program. I'm just going to go through a few examples with showing the capabilities of CHAMP. So one is CHAMP can give accurate excited state properties, and it does this using variation of Monte Carlo wave function optimization. And it can also do fixed node diffusion Monte Carlo to provide more accurate energies. It uses as a trial wave function a Jastrow-Slater wave function, and where the Slater part can be a multi-determinant expansion. It can it can optimize excited states with any symmetry. I say this because if the excited state has the same symmetry as the ground state, you can run into some difficulties, and I'll explain that on the next slide. So over here, we just have an example of vertical excitation energy in this molecule. Here's the values calculated with VMC and DMC using two different types of trial wave functions. Here are the values found with some multi-configurational quantum chemistry methods. And here are some coupled cluster methods. And CC3 is expected to give reliable values for this excitation. And you can see the VMC and DMC results with the CIPC trial wave function are in good agreement with those. And these excited state properties can be calculated with embedding as well. So with the electrostatic environments, and there's also a PCM model implemented as well. I'm not going to give specific examples on that, but I just wanted to add that in there. So one specific type of excitation, which is expensive to calculate in a lot of different methods, are double excitations, and that's because you need high order excited determinants in your expansion. Specifically for variation of Monte Carlo, it's a difficulty because this type of excitation has the same symmetry as the ground state. And if you optimize that state to its variational minimum, you'll go to ground state. So if you don't do something to prevent that, you're just going to end up with the ground state and not the state you're interested in. So we recently implemented this state-specific optimization with an overlap penalty to stop this from happening. And the way this is the flow chart of how we do this type of calculation and why TREX is very useful to do them. So we usually start with the games calculation. We do a CAS SCF to get the orbitals. Then we do a CIPC calculation and quantum package to get the determinant expansion. And then we use TREX tools to convert the outputs into the appropriate inputs for CHAMP. And then we provide our own Jastrow factor to complete the trial wave function. And so we did this for double excitation in this molecule tetrazine. We used this method to do the VMC optimization, and then we performed fixed node diffusion Monte Carlo. And these are the resulting excitation energies for different length CIPC expansions. Again, we have a couple cluster values for this excitation up to triples, which aren't expected to give a good value for this type of excitation. Here's the multi-configurational values again, and you can see that there was a 2 electron volt discrepancy for these. But recently there was a CC4 calculation done, which is expected to give reliable values for this type of excitation. And you can see that the values we got with this CIPC QMC wave functions are in good agreement. Finally,
CHAMP can also do geometry optimization in the excited state. So in the last few slides, I was showing vertical excitation energies, where we optimize the excited state in the optimal ground state geometry. But we're also interested in this adiabatic excitation energy, where we need the optimal excited state geometry, which in some cases can differ very much from the optimal ground state. So in this molecule, the excited state optimal geometry is has a buckling with respect to the ground state geometry, similar for this molecule. In this molecule, there's a stretching of the bond in the excited state. And so we've plotted here just basically the bond length, which agreed the worst with our reference bond lengths. And so the VMC is shown in red, where we optimize the geometries, and you can see the disagreement is always less than 0.01 angstrom, which is good. So that's it. Thank you for your attention.
Thank you very much, Stuart. Okay, we're done. So while you're still here, and thank you very much for those who stayed until the end, I kindly ask you to spend 1 minute more just filling in the survey that you should see on Zoom. It's very quick, and it simply will allow us to better organize the next meetings. And while you do so, I'm happy to give you an overview of the upcoming events. Let me see if I can share this. Yes, can you see them? The slide? Yeah, great. So the upcoming events, the training events that you've learned from our colleagues before. So the next in time is an hackathon that we are organizing in Bologna at Seneca premises for the TREX consortium. Then in April, you're all welcome to join the TREX workshop on electronic structure methods for strong correlation, organized by Kasia and her team that you've met today. This is open to everybody, so feel free to register and join us. Then in June, there will be another workshop in Bratislava in Slovakia about code tuning for the Exascale, again organized by the Slovak Academy of Sciences, who is one of the partners of TREX, open to the consortium and to all externals interested in joining. And in July, as Kozuke mentioned, there will be the TREX school on QMC with the Turbo RVB, where the official Turbo RVB code will also be launched. So it will be an occasion to learn the theory behind quantum Monte Carlo and try and employ these techniques to solve some of the problems using the Turbo RVB QMC package. So you learn more over the next weeks. So if you want to stay tuned, register to the TREX newsletter, and feel free to contact us or the speakers that you can find their contacts on our website directly on the TREX-coe.eu. So we hope you find this webinar useful. And with that, I thank you all very much for your participation, and let's stay in touch. And a special thanks also to all our speakers today. Thank you very much, and enjoy the rest of the evening.